Hi, and yeah. um, I will try to solve this second division round. With some commentary, I hope. So let's go. I don't know what this word means. So basically this problem asks to intersect two segments on the line. That's an interesting problem. We have a one segment, and for the second segment we're given its center and half length, and we should print the length of the part of first segment which is not inside the second one. Why? Just why should we do that? So the intersection of two segments on a line is like its left coordinate is the rightmost of left coordinates of these two segments, and its right coordinate is the leftmost of right coordinates. It can happen that intersection is empty and we will get like negative length intersection, so we should take maximum. So our answer is length of first segment minus length of intersection, which is maximum of 0, and minimum of R1 and R2 minus maximum of R1 and R2. Probably I didn't close, but one more very fresh problem. We have some items with prices. I guess like we could either just buy one item, or we can buy one item and get k-1. Like take k items and pay only the maximum of their costs, not the sum. And we're given how much money we have in the beginning, and we should say how much items could we buy. Okay. So we should sort all the items by price, and if we want to buy some fixed set of items, let's just say we want to check if we could buy all of them. Like we could use some groups of size k, and obviously, like it doesn't make sense to pay for to buy as one item more than k items, because otherwise we could merge them in one group and pay only the maximum, not the sum of their prices. Actually, like it doesn't make sense if they're k items. So we should do this only for n modular k items. All others should be divided in groups, and like it is easy to see that we should pay for n modular k smallest items, and then for each case item in the sorted order, and we will be good. If we want to if we don't want to buy all the items, obviously we should buy the cheap ones, so it should be the prefix in sorted order. It isn't true that we could use binary search on answer, because it can turn out that if n modular k is big, we will pay for many small items, but when for example n modular k is 0, we would just pay for n divided by k groups, and it can be cheaper. But if we fix the number of groups, then binary search works, for example, and obviously we want first to maximize the number of groups, and like with given number of groups, it's cheaper to buy like when n modular k is 0, and if it holds, then it's easy to check like what is the largest number of groups we can pay. We just pay for each case item, and we should just go and do like linear search, but we shouldn't calculate cost in linear time, we could just use the cost from previous iteration and add the next item. Like in the first iteration, it will be case item, then the item number 2k, then 3k, and so on. So first we calculate how many groups we could buy, and then, for example, we can do binary search. I'm sure we can do some other stuff, but binary search works. So let's do binary search. There is a linear solution. Actually, yeah, let's do linear solution in educational purposes. Well, we should do the sorting, so it's not really linear. But let's do linear after sorting. So at first we want to maximize the number of groups. Number of groups, current cost 0, while times -1, because I'm using zero indexation, so yeah, here is this one. So the first item will be k-1, then 2k-1, then 3k-1, and so on. Is strictly less than n. Like this item exists, we could buy such number of groups, and all the items we are paying for are not too expensive. We could increase the number of groups. Now we know that we are buying G full groups. We couldn't buy G plus 1, so we are buying G full groups, and now we want to check how much additional items we could buy. So how to do this? I just want to do linear search. I want to check all the possible answers. How to check how much money do I need for a possible answer? Like I know I will pay for G groups, but I also have to buy some prefix of items for full price, like buying for each one of them. For this prefix, I can maintain the cost just like I did here. I don't even need this array. I will just maintain how much my prefix costs. And then I should also buy for the largest item in all my G groups. I could just go and calculate the sum, because like I will do it in time proportional to n divided by k, and I have to check k possible answers, so the total time will be linear. So P is the last item I'm buying for full cost. And now I'm going for G groups. It could happen that if we pay for P items, there are no G groups left, but so we should also check here that is P plus K times G is strictly less than N. I think that's the ID of last item I will be buying. So yeah, here I can do this, and like the item number P is the last one I bought for full cost, and the next will be P plus K, then P plus 2K, and so on. If we have enough money, then we can update the answer. Don't work on first one. Again, it's not correct. Why is it? Oh, because I'm not increasing cost. Yeah. So yeah, now the answer is correct. I think that for this version, binary search actually works. So maybe it's kind of good to have this subtask. Maybe not. So in this problem, there is an exam which lasts 40 minutes. There are two types of problems. Easy problems which require A minutes to solve, and hard problems that requires B minutes to solve. Also, for each problem, we know some time which means this, like we can leave the exam at any point. We should probably choose the time when we will leave the exam in advance. It should be not greater than this like time of whole exam. Let's say that this time is L for leave. So for problems that have this parameter t not greater than L, our time when we will leave, we have to solve them, otherwise our result is 0, and it's not interesting. We can get 0 just by leaving at time 0. So we have to solve all of these problems, and we can also solve other problems. Okay, and our goal is to solve as many problems as we can. So the solution is kind of inferred from the statement. We have to choose the time to leave. Okay, suppose we have fixed this time. Okay, so this way there are some problems that we have to solve. Just count the time needed to solve all of these problems. If it's greater than L, then we cannot do this, so the result will be 0. Otherwise, we can do this, and we have some time to spare. And there are also some problems that are non-mandatory, and we just want to solve as many of them as possible. We will start from easy ones and then go to hard. We know how much easy and hard problems left, and we can just calculate the count in constant time. Okay. Then we just want to try all the interesting values of t, of L, the time to leave. It doesn't make sense to leave if we could just sit for 1 more minute and no problems will become mandatory. So interesting times are the times when, like, in the next minute some problem will become mandatory, or like the whole exam. It's also interesting time because we cannot wait long. So there is linear number of times to check, and we should somehow calculate the sum of like the number of easy and hard problems which became mandatory to this point. We could use something like lower bounds, but we could just sort all the interesting times. Like, we could just sort all the problems by the time they become mandatory, and like go from left to right, and just maintain the sum of times, how many easy problems left, how many hard problems are left, and we just like try okay, this will be the first, like we are going from left to right and say, okay, this will be the first problem which is not mandatory for us. So we know how much time do we have, and like we will leave at point like the time this problem become mandatory -1. It can happen that like some problems we are saying that they're mandatory, but it's actually not true because they had the same time as like this problem we're looking for, but it couldn't like increase our result, so it's okay. And yes, then we can check all the possible variants in constant time. There are a linear number of them, so total solution is again linear after sorting. We have to sort the events, and then it will become linear. We have multitask because so we have to set the 0 explicitly. We want to know how much easy and hard problems there are, so we will calculate them. This will be second because I want to sort by time, and this will be the first parameter. I also want to check like the end of exam. So I will say that the last, like after all the problems, there will be one more problem with time t+1. So this time -1 will be the end of exam, and it will have type -1. So I will not forget about this probably. So we have sorted everything. Answer is set to 0, and okay, we are going. Also, there is time that we have to spend on mandatory problems. If it is strictly greater than this time -1, then like it's the bad situation. We cannot do all the mandatory problems in time. So like the interesting situation, if it is not more than this thing, then we have to calculate something and calculate like the number of problems. Okay. So the time we have is the difference of these two values. And we have easy problems and hard problems. So like after this I will decrease this value. Okay, to solve all easy problems we have to spend e times a time. If it is bigger than the time we have, we will solve only easy problems. So let's say the answer is only 1 because we'll use maximum and C++ don't like this. So we will solve we will solve only easy problems, and how much time we have this time, how much problems we will solve. Well, easy, it's this divided by the time we need to solve one. So we have to update answer with what? Like we can solve this number of easy problems, but actually we have solved some mandatory problems. How many? I say that's I. Like the i's problem is the first one that is not mandatory. So this. And yeah, so all the previous are mandatory and we solved I of them. And otherwise, we will solve all easy problems and then move to hard ones. So we have solved I mandatory problems, then E easy ones, and then we have this much time on hard ones. So we will solve this many of them, but this is actually not true. We will solve no more than like how many hard problems left. So we have to take minimum here. Okay, now this problem becomes mandatory. I guess I could say that the last one is also hard, so I don't need this if, just else. It will be okay. Whoa, that's some cool problem setting techniques from Mike Mirzianov himself. Okay, if this problem is easy, then we have to spend a more means, and we have one less easy problem, and otherwise we have to spend B means more, and we have one hard problem less, and print the answer, and we're done. So the answer starts here actually, and it is correct. This is what happens when you don't have actual coordinator. Interactive problem. Cool. She is accepted. Okay, so there is a non-empty string of letters A and B, which is not known to us. It is known that it is like its length is n, and it is between 1 and 300, and n is not known actually. But like the number of queries depends on n. So we can ask some other strings, also non-empty, and the answer to our query is the edit distance, so the minimum number of operations of replacing, inserting, or deleting characters to get like, one string from the other. Okay, so we can ask some strings. The answer is edit distance. And we can ask no more than n plus 2 queries, and like we should guess the string, and it's easy to see that like the only string that have a distance of 0 is the string we want to guess. So we have to like get 0 as an answer. And this query also is included in this n plus 2. Okay. Okay, this looks like interesting problem. The first one in this contest, and possibly the last. When the number of queries dependent on the length of answers that we don't know, and like possibly we should start from some short queries so that if the answer is short, we could guess it quickly. Maybe we could start from some query and then continuing to like increase the number of letters in the query so that if the answer string stopped to grow, we could understand that. For example, we could start from like query A, and it's easy to see that edit distance cannot be less than the absolute value of difference of length. And if our query is a subsequence of the string we are trying to guess. If let's say that string, according to statement, the string we are trying to guess is S and our query is T. So if T is a subsequence of S, then the answer will be just difference, like length of S minus length of T. So if string S has letter A inside of it, then the answer will be length minus 1. Otherwise, the answer will be just length. We have to change this A to B and add some number of B's to get the string S. So we could just ask A and B in the beginning. If the answers are different, then we just know that the string is either all A's or all B's, and we know the length, so we could just guess it. So otherwise, the answers will be the same, and in both cases, it will be length minus 1. Okay, so we know the length. We know n. Unfortunately, edit distance is somewhat hard. It could happen that deleting one symbol and inserting the other is taking much less operations than replacing symbols. Like if we have the query of the same length, it is not guaranteed that the edit distance is just Hamming distance, like just the number of positions in which the strings differ. Because it may happen that insertion is like deleted in some place and insertion in the other place, like it shifts some part of the string, and it can be good to use such operations. But, like, for example, if we, like, now we know the length, we could, for example, make the query of length n, which is all A's. For this case, the edit distance is just number of B's in our string, because we have to do at least that many operations, because each operation can increase number of B's at most by 1. So we have to do the number of B's, and it's possible because we could just replace replace some A's with B's in the places we want to. So after these 3 queries, we know the number of A's and B's in our string. after that, I think we can do something like change 1a to b. Um, if we get the right spot, like there is actually b and not a in the spot, then the edit distance will decrease by 1. Like now we have to replace all the other b's, which is like their number is decreased by 1. But it could happen that our replacement was actually like kind of good, because now we can use some inserting and deleting, but actually deleting cannot increase the number of b's. So there will be at least one operation which doesn't increase the number of b's. So we have to do at least like the old answer -1 replacing and inserting, and 1 deleting, which will not make the answer better. So I want to say that let's say that the answer for string of all a's was C, and if we change 1a to b, then if it was really b in this place, then the answer will be C-1, and otherwise it will be C or maybe even more than that. Not more than C+1, but C or C+1, but not C-1. So we could just check every position. And I guess this works in n plus some constant which is too big number of queries. Like we spent 2 queries on A and B, then we spent 1 query on all A's, then we spent n queries on checking all the positions, and then 1 more query to print the answer. In guess we could use n-1 queries to check all the positions, because we know the number of A and B's. So we don't have to check the last one. We could just print the answer right away. So it's n plus 3 now, and we want n plus 2. I guess asking A and B in the beginning is kind of redundant. Not at all redundant, but like most of the strings have A's and B's. So when we ask A, like we get some answer. Let's say it's D, and then we know like either the length of the answer is actually D plus 1 and it has A's, or the length of answer is D and it all consists of B's. Can we somehow distinguish between these two cases, not spending 1 more query and just like somehow starting our solution, like assuming it's the length of answer is D plus 1 and it's all consists it all of A's. it has some a's. Sorry. Like our next action was just creating a string of length d+1 because it's n of all a's or of all b's, if that's a matter. Okay, let's assume it's all a's and it has length n+1. Then if n is actually d+1, then the answer will be the number of b's in this string, and this will be strictly less than d+1 because it has at least one a. And if the actual answer is string of all b's of length d, then the answer will be d+1. We have to erase all a's, either by replacing or deleting, but we have to do d+1 operations, and like the answer is actually d+1. So, delete one a and replace all others to b. So after that, if we get answer d+1, then we know that the answer is just the string of all b's of length d, and we could just print it out. And we spent 3 queries, which is not more than n+2 for n at least 1, which is it is. And otherwise, we just starting our solution, and we are good with n+2 queries. That's great. Once again, I highly recommend to write the special function for query, so that it will be the only place where you should like do flush and stuff, and it's convenient to use. Like you're just using this function as an the only way to interact with the system. And for example, like interactive problems are harder to test because like you should produce real answers, and it often happens that like your solution doing many like redundant work. Even on small cases, it asks many questions, and it is hard to do. So basically, many time you want to implement the interactor, and it is often useful to just implement the interactor inside the solution and just change this function. Like it just asks the query, and you can change inside of this function to like calculate the answer to the query, assuming that you like know the answer, which is like starting some variable, and not actually reading it from input. So to do the query, we should just out this thing, and I will use handle. This does flush automatically. So I plan to query A, then create a string of all A's. this thing. If it is d plus 1, then actually the answer is string of length d, all of letters b. I guess it should happen. Is not adaptive. Interesting. It could happen that we accidentally guess the string inside this query thing. So if it returns 0, then we should do exit 0, because otherwise, like, it probably says somewhere here, after breaking the rule, your program should end immediately. Okay. You don't actually. Like, yeah, we should do this query and then just throw, because it is either get 0 and do exit 0 here, or just it's not 0, and this shouldn't happen. Okay, then we can create string ans, which is for now it's all A's, and C is the number of letters B in the answer, and D will maintain like how many letters B are left. Now we should do this. Ask all the queries. So we get the string with all A's except the is symbol and query it. If the answer to the query is strictly less than C, then it is actually B, and otherwise it is not. And then we should return to A, just that we maintain that string S is always consists only of letter A. So in this case, we should do this and decrease D. If D is less than 0 or greater than 1, this shouldn't happen. And if D is 1, then the last symbol is also B. Otherwise, it's A, and it is A now. And we do query and throw. Yeah. Hey. Okay, so let's say that this was. So the answer is 4. Now it is 2. Now, I don't know. Maybe it is like it's 2 or 3. Let's say 3. Let's say 2. Now it's 1. Now it's 1. And now it's 0. Okay. 2. Yeah. Pretty good. Okay, so in this problem we had convex unsided polygon. Then n minus 3 times they take a diagonal that cuts one triangle and delete this triangle. So you can see the process. The vertices were numbered in some order. Now we are given n minus 2 triangles and we want to restore some way to enumerate the vertices of initial polygon and then the order of in which the cuts were made, the order of triangles in which they were produced, so that we get the given triangles in the result, and it's guaranteed that the answer exists. I wanna say that we should just find the vertex that that appears only once in all of these triangles and say that the first cut was such that we erase this vertex. And then we delete the triangle in which it appears. I think that it is true. Why wouldn't it be? Yeah, when something is a diagonal, yeah, we can look at this picture. We have some sides of the triangles which were sides of initial polygon, and we also have sides that are diagonals. I want to say that side is a diagonal if it is a side of two triangles, and it is a side of initial polygon if it is side of one triangle. So yeah, when a vertex will be an endpoint of some diagonal, it appears at least twice. In this diagonal will be in two different triangles, so this vertex will appear at least twice. And otherwise, it will appear once, and we could just cut it. So yeah, restoring the order of triangles is easy. We'll just maintain for each vertex, like the number of times it appears, and we will have to find the triangle in which it appears once. So we will, for each vertex, we will maintain, like, not the list, we will calculate the list of triangles, and then we will maintain the number of times it appears. Then we will do like something BFS-like. We have to take a vertex which appears once, then find the triangle in which it appears once. To do that, we will just scan the list of triangles it appeared, and like for some triangles, it will be marked as already erased, and there will be only one that is still alive, and then we will mark it as erased and put it in the order. We will mark triangle as erased, decrease the number of appearances for all its three endpoints, and it can happen that some endpoint has also become like only once, and to do all this, we will maintain a queue in which there will be the vertices which now has only one appearance, and we are going in this queue from left to right, take a vertex, find a triangle, mark is at erased, mark it as erased, decrease the number of appearances of all the endpoints, and if some endpoint become exactly one appearance now, then we will put them in queue. Afterwards, we should find the order. For this, we could like the order of vertices in the initial polygon. We could just add, like when we erase a vertex, like the order of all others will remain the same. For example, going from here to here, we want to erase 2, and the order of all others will remain the same. So we will restore it going backwards. Like we start from some triangle, and then we want to place one triangle back. We place one vertex back, and we know its neighbors. So we'll maintain a cyclic order. For example, we can do it in linked list. Each vertex will point to the next one in our order. To insert a new vertex in this linked list, we want to know these two vertices and like check in each. We know that they are neighbors in current order. If it's not true, then something has broken, and this shouldn't happen. We should check in which order they're like. We should just say that it is either after this or after this. Which one to choose? Like we want to choose this if the next one is the second pair. And then we will get the whole cycle in linked list, and we will restore everything. And the whole solution has linear time complexity. Reading all the triangles. Creating a list of all triangles for each vertex. Increasing the number of alive triangles. In the beginning, all the vertices and all the triangles are alive. We will also have some queue. So if a vertex has only one occurrence, then it goes to Q. We will erase exactly n-2 vertices. Like by idea, the arrays ans and ans2 are like the arrays we have to print. But like we can construct the array ans2. Okay, we will construct array ans2 first. It's the order of triangles. The array ans will be constructed using our linked list. I wanted to use it like to write the vertex we have deleted on this iteration, but actually they're written in array Q, so we don't have to reuse array ans. Okay. So we know that vertex V has exactly one triangle alive. So function find alive will find this triangle. Now I want to kill it. To do this, we say that the life is false, and we have to like for all 3 endpoints of our triangle, we should decrease the number of occurrences. Let's take the endpoint, decrease the number of occurrences, and if it has become exactly 1, then we should add it to Q. So how to understand what vertices remain? We could find for what vertices this is not true, but actually the last vertices in Q. So good job to this. Oh, we also want to say that ans2 of I is id plus 1. Let's use id and do plus 1, but we will print it. Okay, so now we are going backwards. We know that triangle ans2 of I was deleted, and the vertex we should return is vertex Q of I. Now we have to find the other 2 vertices in this triangle, the ones that are not V. So if this is V, just do nothing. And otherwise, if we didn't find the first one, then it will be the first one, and otherwise it will be the second one. If next of U is V, then we should swap them. We know that for one of them, for at least one of them, the next should be like the other one. If it's not the case, then something went really bad. And now like we should insert v such that like the previous one, the previous and the next one are both u and v. V is the next of u, so it will be in order u, v, w. So next of v should be w and next of u should be v. Okay, and now we have to print them in some order. It should be circle of length exactly n. You could just print them here, just not using additional array, but it's fine. Yeah, I have to write a function find all. That's easy, it just goes all of them. And if it is alive, return. There should be at least one. Like there should be exactly one, but cool. So I guess it's not working even on first sample. Okay. Is it true that first sample is this? Yeah, it looks like it. Okay, so I'm saying that I can delete 1, 2, 3, 4, that's 2. Oh, I should start with elements. It looks correct. Yay. So this contest had one good problem. Problem D is kind of fine. ABC is pure garbage. and E is not very fresh and also not very interesting. G was fine. Thanks for watching.